Okay, I'm going to continue the lecture 4.4. Some of the stuff we didn't get to cover in live class. So specifically the proof for the unique representation theorem, and then a more detailed example that's going to give us the definition for a change of coordinates matrix. So that's going to be pretty important. Let me get the theorem up here. So theorem is the unique representation theorem. You should already have this in your notes from lecture, but I'm reproducing it here for reference. Let script v equal b1 through bn be a basis for a vector space v. Then for all vectors x in my vector space, there exists unique weights or coordinates c1 through cn in R such that the vector x is a linear combination of those. So c1, b1 plus down to cn, bn. Okay, so what makes this proof, it's the first time that we're introducing a new proof technique. That's going to be kind of the crux of the matter, and which is going to be the proof by contradiction. So I'm going to spend a lot of time explaining that to make sure all the pieces logically make sense for you. Otherwise, it is pretty routine to what we've been doing in this class. So let's declare variables to get our stuff. So let script b equal to b1 to bn be a basis. So this is a basis for v, a vector space. And then now, what do we want to show, right? So want to show that for all x in v, that there exists unique. Remember, the exclamation point is unique. The word unique is indicated by the exclamation point. So there exists unique c1 to cn in R, such that I could write my vector x as c1, cn, linear combination. c1, b1 plus, and then cn, bn, right? Okay, so two things. Whenever we do a uniqueness proof, showing uniqueness of something is usually going to involve two parts. The first part is just showing that it even exists in the first place. So we want to guarantee existence. There's no point in doing unique existence if the existence isn't even guaranteed. So we'll show that the existence is guaranteed, and once we've done that, then that's when we introduce this new proof technique called proof by contradiction. And that is going to be the logical method that we're going to go about guaranteeing that not only does it exist, but it exists uniquely, it's distinct. There's only one version of it, basically per vector. So let's do the existence in general. The definition, and we can do this definitionally, right? Because think about it. That's just a linear combination. Well, didn't we know that the definition of basis itself basically say the span of my basis should produce the vector space that I'm spanning, right? If B is a basis for V, then definitionally V is just the span of whatever all the vectors in B are. So we will obviously have a linear combination to access my x. Because otherwise, if that wasn't true, if I wasn't able to get an x that was a linear combination of my basis vectors, it wouldn't even be definitionally a basis. It would fail its own definition. So we can cite the definition of basis here. The definition of basis basically guarantees the existence of these scalars. So guarantees, we could say it this way, guarantees the existence of scalars C1 through Cn such that x can be written as a linear combination of the basis vectors. Again, that's entirely just by the definition of basis. So if you're struggling to see that, make sure you know and review the definition of basis straight away. Make sure you have that in your notes, reference it, make sure that you can make that definitional connection, okay? Alrighty, so, and this is actually true for all x in V. So this is just an important little caveat, right? So I could always find these linear combinations for any vector I chose. And that's by definition. So, thus, that reduces now the problem to showing uniqueness. So we've guaranteed that these things are going to exist. We know we can get these linear combinations, but are those linear combinations unique? Are they distinct for this basis? That's the real question. Thus, we must show that this linear combination, with my C's combination is unique for my vector x. So we proceed with a proof by contradiction. What is proof by contradiction? Proof by contradiction is going to be this. Let's say that I'm going to assume some statement is true. So I'm going to assume some statement is true. Why would I do that? Well, I'm trying to prove something to be true. So if I'm trying to prove that a statement is true, then what you can do is this functions as a reasonable proof. You simply, in your own proof, you assume the exact opposite conclusion that you want to reach. Okay, so you assume basically precisely the opposite of what you're trying to show. And you just assume that. You say, okay, let's just say, hypothetically, that the complete opposite statement is actually true. And then what happens is you go through the logical ramifications of making such a presupposition, like accepting the opposite of your own conclusion. And then if you can get it to a point where it will definitionally contradict itself, hence contradiction, if it is inherently contradictory and logically flawed, that means that all the way at the top of the chain of command, that first domino that fell was a false presupposition. That we assumed something false that led us to get to something that's definitionally inconsistent or logically inconsistent or a contradiction. So if that then fails, that forces the opposite of that statement to be true, meaning that then we've basically proven what we wanted to prove. So that's the premise here. If we're trying to show that some statement P is in fact true, let's assume from the get-go that the opposite of P is true. And we accept that the opposite of P is true for the sake of contradiction, demonstrate how doing so results in a logical contradiction. And if that happens, then we have effectively demonstrated that, okay, well, ergo, we cannot assume the false presupposition. So that probably makes no sense in just words. So if that was a word salad that frankly doesn't help whatsoever, I will keep annotating the logic of it as we go through this proof, okay? It makes a lot more sense with an example. But this is a general proof technique that works in a lot of different cases, and most uniqueness theorems that we have, in some sense, invoke proof by contradiction. Okay, so let's see here. Here's the thing. What am I trying to show in this specific theorem? I'm trying to show that that selection of C1 through Cn, that selection of coordinates, is completely unique for every single vector. So each vector has its own unique address, basically. So if that's what I'm trying to prove, I'm trying to prove that each vector has its own unique address. And so keep that in mind. So that's what I'm ultimately trying to prove. I'm trying to prove that there is unique address. So for a contradiction, I'm going to just now default assume the opposite. So I'm going to assume, for the sake of contradiction, that, oh no, actually, that it's not unique. That representation is not unique. I could find another set of scalars, let's call them like say d1 through dn, I could find another set of scalars such that I could still get to x. And it would be, I could get to x using completely different coordinates. We're not trying to prove that. It's the opposite of what the theorem is actually trying to state. But that's why we're doing it with contradiction. So, assume, let's see here. Yeah, assume, and I'll put a little hashtag right here to indicate that what we're about to assume is precisely the opposite of what the theorem is ultimately about. Okay, we're now going to embrace this incorrect perspective and demonstrate that this incorrect perspective is incorrect, thereby verifying the opposite of it. So, assume that our x, which is equal to c1 b1 plus to cn bn, assume that this linear combination is not unique, is not a unique linear combination. Linear combination for x. So this is precisely the opposite of what we're trying to show. Then, if I'm saying that this is not unique, then that means I can find some other scalars. So that means there would exist some other scalars d1 through dn in R, such that I could write x also as d1 b1 plus 2 dn bn. Alright, so here's the hashtag indicates the beginning of the assuming the opposite statement. We're going to assume that this is not unique, and so, therefore, I could find some other scalars d1 through dn that also get me x, okay? So here's what we kind of do, which is kind of clever. So we show that now, think about it. If I have the vector x that can be achieved by using the coordinate c1 through d1, And there's also this other set of coordinates d1 through dn that also get me to x. Well, ultimately, x minus x should still just return me to the 0 vector, right? If I take a vector and subtract from itself, it gets to the 0 vector. So I know that the 0 vector is x minus x. Now you might be thinking, wow, how on earth is that showing anything? Well, take a look. Let's now plug in both representations. So let's take the first representation with the C1 scalars. So we got C1 B1 plus to Cn Bn minus, and then now let's do this, this other set of coordinates, right? Because we're assuming that it's not unique. Ergo, let's take the other representation. D1 B1 through dn bn. And if I take C1 and subtract it like this, then simplifying this algebraically, I'm going to get this linear combination, right? C1 minus D1 for B1. And then I subtract all of the corresponding coefficients to the end, Cn minus Dn times Bn. Now the key here is to recognize that this right here is itself a linear combination. How do I know that? Well, because C1 and D1 are just scalars. So if I subtract two scalars from each other, that's just a new scalar. And we saw this logic a lot in the previous unit for when we did proofs. So a scalar times one of the vectors plus a scalar times another one of the vectors, etc. This is just a linear combination of the basis vectors B. Okay? And then, really, really importantly, this linear combination of basis vectors is equal to 0. Okay, that's going to be the key observation to make. That this specific linear combination is equal to 0 vector. The definition that should come to mind immediately is linear independence. What happens if I take a linear combination of vectors and set it equal to the 0 vector? If they are truly linearly independent, then by definition, the only possible solution is the trivial solution. So if that doesn't click yet, go back in your notes right now, turn all the way back to Unit 1 when we defined linearly independent for the first time. And when we defined linear independent for the first time, the way we defined it was we said, if I take a set of vectors and set it equal in linear, if I take a linear combination of vectors and I set it equal to 0 vector, if the only possible solution for that is the trivial solution, that means that set of vectors is what we call linearly independent. So here I have a linear combination of vectors set equal to 0, and now it's just in a different order. I know that B1 through Bn, those are basis vectors, and basis vectors, by definition, are required to be linearly independent. Think about that. So now turn in your note, if you don't remember off the top of your head, go to the definition of basis itself, how we define the basis. The very first property under the definition of basis was that we require all of the basis vectors to be a linearly independent set. All the basis vectors have to be linearly independent of each other, okay? So that's why I know B1 through Bn are linearly independent. They have to be. They're required to be by definition if it's a basis. So since B1 through Bn are required by definition to be linearly independent, and we've shown that this linear combination of them is equal to the 0 vector, there's only one conclusion we can reach here, and it's that only the trivial solution is possible, okay? The only way for this equation to actually be true is if all of the weights are equal to 0. That is, we have the trivial solution only. Okay, so that's a lot. There's a lot of concepts floating around there, but if you really understand the definition of basis, and you really understand the definition of linear independent, then what I'm about to write is going to make a lot of sense. Okay, so if it doesn't, review those definitions and really think about it until it does. But for now, I'll move on. So So here's how I can articulate this in a proof. So since the basis B, rewrite that. Since B is a linearly independent, how do I know that? Well, because that's just definition, literally by definition. So I'll put that in parentheses, by definition. The only way that this thing here, so C1 minus D1 times B1 plus all the way down to Cn minus Dn times Bn, the only way that that is equal to the zero vector is if all the weights are zero. All the weights are zero, which is basically the only the trivial solution. And again, we're getting that only the trivial solution by the definition of linearly independent. That is, so now I can reframe that in terms of what my actual expression is. So that is, if all of the weights are equal to zero, what are the weights? The weights are these C1 minus D1, blah, 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 right? So Ci minus Di is equal to zero. Each one of these weights, Ci minus Di all the way down, is equal to zero, which implies, obviously, that Ci is equal to Di. And that's going to be true for all of the i's from 1 to n. Okay, so that's kind of the logic here. We assume that this is not unique. And if we're going to assume that this is not unique, then there has to exist some other set of scalars that make a different linear combination. And so, the zero vector is what I just do if I subtract the vector from itself using the two different so-called, different representations. And in so doing, we get a linear combination. But this linear combination itself is equal to zero, which sets us up to use what we know about linear independence to say that, okay, well, the only way that this works is if the trivial solution is the only possible solution. Ergo, every single weight must be zero. So each Ci minus Di has to be zero. But just algebraically manipulate that. That's basically saying that Ci is the same exact thing as Di. Ci equals Di. These coordinates are forced logically to be the same thing for every single I1 through n. Okay, that's a problem though. This is logically contradicting our assumption here that it's not unique. So think about it. If we started by assuming that this is not unique, and assuming that it's not unique resulted in the conclusion that they are the same representations, that's logically flawed. That's a logically contradictory conclusion to reach. That means that whatever we just assumed here is false. What we assumed here cannot be true, because if it were true, we wouldn't be in a logical contradiction. So by assuming this here at the hashtag, by assuming this, we reach a logical contradiction. We reach the conclusion that these distinct Di was supposed to be distinct from Ci, but we showed that, they actually have to be the same exact thing. Okay, That's in direct contradiction to this statement here. If you have a logical contradiction, that means whatever you assumed to cause it to break is false. So if that means the statement here with the hashtag is a false statement, ergo, the opposite is true. So that means that instead of this not being unique, it is in fact unique. So here's, I can kind of try to summarize this a little bit in writing so you have it. But here, is a contradiction. We assumed that x is equal to c1b1 plus cnbn. We assumed that that was not unique. But by doing so, like the act of making that assumption produced the opposite conclusion, which is kind of funny. So, but by doing so, we have shown precisely the opposite. Okay, think about that. There's a contradiction, right? We assumed that this was not unique. But the very act of assuming that it's not unique produced that, showing that they actually have to be the same. So that we showed the opposite statement. We assumed this to be true, and then by doing so, ended up showing the opposite of what was supposed to be true. Contradiction. So ergo, whatever we assumed has to be false. Therefore, our assumption must be logically false. That is, it is logically contradictory, so logically contradictory to claim that x equals c1b1 plus plus cnbn is not unique. So, think about it. If it is logically contradictory to claim that this is not unique, then the opposite has to be true. So, it is, in fact, unique. So we have shown uniqueness of these linear combinations by assuming the opposite. Aesthetically, I'm just very pleased by how that looks on the whiteboard. It ends on the same line. That's kind of nice. Entirely unrelated to the problem. I just think that's nice. Okay. Alright, that's a tricky proof because it's the first time you're doing proof by contradiction in this class. So if it feels confusing, then yeah, that's a very normal, probably, feeling right now. So take time with it, study it, walk yourself through it, the worst thing that's going to happen is not really the logic part of it, but the definitions and just not seeing how the definitions play into it. So review the definitions, okay? Know your definitions so well, because if the more familiar you are with those properties and definitions, the reasons why we're able to make conclusions is just going to make that much more sense. Okay, let's do now a computational practical example here, get away from all of this horrendous theory. Although actually I think it's beautiful, but it's a subjective opinion, I suppose. Okay. Board reset. Example. Let's define some vectors here. B1 is equal to 2, 1. B2 is equal to negative 1, 1. And some vector x is 4, 5. Now, let's say that B1 and B2 are a basis. So let's find, and I should state a basis for what, to be precise here. It's a basis for R2. B is a basis for R2. Okay. So, let's take a look here. We want to find the coordinate vector, x b of x relative to this basis. Okay, so what is this problem saying? This problem is saying this. There is this point 4, 5, this vector 4, 5 in the standard representation. So how we normally think of 4, 5 with just in R2. So actually I can graphically do this if I'm careful. Here's x1, here's x2. And so this is the 0 vector here at the origin. And then there's going to be these grid lines. 1, 2, 3, 4, 5. I'll try to do it as accurately as possible here. And then 1, 2, 3, 4, 5. All right, so it's not perfect. Sorry. That's close. So this is the plane R2. This is the current perspective. Notice that my basis vectors for this perspective are E1, which is 1, 0, and E2, which is, so here's my, this is this standard perspective. So this is our standard basis for R2, E1, E2, where you can think of those vectors as being 1, 0, and 0, 1. Alright, so that's 1, 0, and 0, 1. So this basis produces grid lines like this. This basis spits out this kind of a grid line structure in R2. And so the vector for 5 is going to be 1, 2, 3, 4. So 1, 2, 3, 4. And then 5 in this direction. 1, 2, 3, 4, 5. So right here is our vector x is equal to 4, 5, which can be thought of as 4 times E1 plus 5 times E2. And those are precisely the basis vectors. So I could think of this as 4E1 plus 5E2 as well. So I go, this is 1, 2, 3, 4, and then this is 1, 2, 3, 4, 5, okay? So within this specific basis perspective, I have this vector x 4, 5. Okay. Now let's take a look at this other basis. This other basis is going to be generated from these vectors, 2, 1, and minus 1, 1. Okay, so if I anchor down an origin here, let me do that like here. So I'm going to anchor down an origin. This is still R2. The first one is 2, 1. Okay, so 2, 1. Like that. So I'm using the same, this is still roughly the same thing, but now I'm going 2, 1 off in this direction. So then my, this is B1. And then my B2 vector is minus 1, 1. Okay, so let me erase this real fast because it's in the way. So minus 1 and what? So minus 1 and minus 1 and up 1. It should be the same height. There. Like that. It's not drawn super well. Let me try again. Because that's the distance 2. That's the distance of 1. So it needs to be a little bit closer in. Like that. There we go. Perfect. Okay. So this is my 0 vector at the origin. And now, what kind of grid lines is this going to produce in the plane? It's going to produce grid lines that look like this. Oh, this is going to be rough, okay? I'll do my best. I'll do my best. And then this is going to produce grid lines like this. Okay, so this isn't the most precise thing in the entire universe, but hopefully it gives you an idea visually of how we've now made our grid lines different. If it extends on this side, so Okay? So, this is still R2, right? But we're using a completely different basis. So these are the grid lines that get spit out if I use my standard basis of E1, E2 for R2. But now I have this basis B comprised of vectors B1 and B2. So this is B1, and this is B2, where the problem obviously has told me what these two vectors are. B1 is 2, 1, and B2 is minus 1, 1. Okay? So think analogously about these two things. This basis spits out that grid line. This basis spits out these grid lines. I'm still talking about R2, so I haven't changed the actual vector space. That's key. I'm still talking about points, vectors in R2. That hasn't changed. The only thing that's changed is the perspective by which I'm now going to access it. It'd be like making different street plans for the same exact area of land in a city. So it's like, do you want your roads and crosswalks to go like this, or do you want your roads and crosswalks to go like this? You're covering the same landmass, but you could access it with different directions, okay? And so now, think about, so the real question is going to be like, what linear combination of these vectors is x? Right? So, let's see. So, relatively speaking, if I were to try to envision it like this. Here's the origin, 0 vector. Here's the origin, 0 vector. The relative distance, okay? So if I were to take this graph and put it on like transparent paper, right? So if I took this graph and I overlaid the two graphs, the origin and the x vector would be exactly lying on top of each other. Okay, that's huge. That's a big concept here. If I were to overlay these two grid lines on top of each other, even though the grid lines are different, 0, if I line it up with the 0 vector here, this x vector should be corresponding exactly to the same location, the same place in my vector space. This vector x here, we may use the coordinates 4, 5, but forget about the coordinates for a second. The vector that happens to be in that space, that particular spot in R2, if I overlay that graph onto here, that's not going to change. I haven't changed its location at all. The location of x is precisely the same in both of these different graphs. The grid lines look visually different, but the actual location of x, that x vector, is exactly the same when R2, okay? So we can represent the same exact object in R2, just now using two completely different linear combinations of basis vectors, okay? Now, the question is, what coordinates in this specific perspective must I take to achieve the same location? So in the standard basis, I happen to need the linear combination 4e1 plus 5e2 to get to this specific location. But now with this basis, with b1 and b2, what linear combination of b1 and b2 do I need to access the same exact location? And the instructions for that linear combination is what we mean by the coordinates, okay? So we can do this. I know that by definition that I have c1 b1 plus c2 b2 is equal to my x, okay? So I know that I don't know what these coordinates are yet, but I'm going to solve for my coordinates. some linear combination of my basis vectors is going to get me to this location of x. So C1 times B1 is 2, 1, and C2, B2 is minus 1, 1. And I know that what I'm trying to get to is 4, 5. I'm trying to get to 4, 5 with respect to the standard. But I'm trying to access it now using a different coordinate system. So we know how to do this with a matrix equation. 2, 1, minus 1, 1. C1, C2 equals 4, 5. And now this has just a linear equation, right? It's a system of equations with a matrix equation. Here's my matrix A. You can do whatever you want with this, but that's not the important part. So I'm going to skip the row reduction and just tell you that we're going to end. If you do it correctly, you'll get C1 equals 3 and C2 is equal to 2. So that means that the vector x is equal to 3 times b1 plus 2 times b2. This linear combination of basis vectors is used to achieve this. Okay? Now let's test that. So think about it. Over here, I needed 4e1 and 5e2 to get to x. Now, to get to x in this basis, I have 3b1 plus 2b2. So let's try it. Let's do 3 of my b1. Okay, so here's my b1 vector right here. I'm going to do 3 of them, because that's what it says right here, 3. So I go 1, 2, 3. So I have 1, 2, 3 of my b1 vectors. Okay? And now I need to do how many of my b2 vectors? I need to do 2 of them. So I can take 2 of my b2 vectors. So the b2 vector goes like this. So I'm going to move along this axis. Okay? So in a similar way to over here, I would move along this axis in the first direction, and then move along this axis in the second direction on those grid lines. I move along those grid lines for the first b1, and now I move along these grid lines. So I'm going to go 2, 1, 2, and bingo, that's exactly what we want. Three copies of the b1 direction on this grid line, and then 2 copies of b2 on this line get me to this. So 3 b1, actually I'll be parallel, so it would be 3 times the b1 vector, which is 2, 1, plus 2 times the minus 1, 1 vector, which is 3b1, 2b2. So now it's completely analogous. So we traveled along different grid lines, but we ended up at the same exact location. And that's what these coordinate systems are doing. We're traveling along different grid lines, so to speak, in the R2, and we're achieving the same place. And once you internalize that, really understand this concept, then you can start abstracting to other vector spaces. But for now, think about it in terms of the plane. Think about it in terms of Rn and what's familiar, until that becomes really solid, and then you have a framework, a base, to then go forward. So, notice this matrix right here, and I kind of hinted to this in the live lecture, that the matrix itself is comprised, its column vectors are just the basis vectors of B. And so this matrix right here, it's effectively taking coordinates in the B1 coordinates, right? Because this C1 and C2 are the B coordinates. These are B coordinates, and it's spitting out the standard matrix coordinates. So in some sense, this matrix is converting B coordinates to standard coordinates. That is, the matrix is changing the coordinates. Okay, so this matrix changes the b coordinates of x into the standard coordinates for x. That is, this matrix right here, 2, 1, minus 1, 1, which is converting, so it's basically the matrix B1, B2, is converting these coordinates, the b coordinates of x. So here's my vector x with respect to b coordinates. So this is this. The C1, C2 are the coordinates of x with respect to my basis b, are spitting out the coordinates of x with respect to e over there. Okay? So we're going, we can generalize this. So I'm going to write the generalization over here because I have more room. So generalize, we want to generalize this example. So generalize example. And it's that script B could now be any size. So not just restricted to 2 vectors, but n vectors. And now we can let some p sub b be equal to this matrix, where I make a matrix by putting the basis vectors as the column. So like over here, this matrix that we put together is really just b1, b2 for our basis. Well, if we had a general number of basis vectors, let's just do b1 through bn and call it this p sub b. Then we have that x is equal to c1b1 plus cnbn, where those c's are the coordinates in b, is equal to this matrix b1 to bn times the c vector c1 to cn. And once we've written that vector equation like that as a matrix equation, that b1 through bn is this p sub b, the matrix where all of the columns are the basis vectors, times just the coordinates of my vector with respect to that specific basis. Okay, this generalization. Okay. So this is a very special type of matrix. Clearly, being able to take the columns of a basis and putting it into a matrix to change the coordinates, that's a really, really special type of matrix. So we want to give that a definition. We'll now formalize that. So as much as I hate to erase this beautiful, beautiful board, I'm going to have to. I'll try to preserve as much as possible. So I'm going to get rid of the standard perspective because that's the easiest perspective to understand, I feel. But I want to keep the other stuff up so you have something to visually reference when I write this out. Okay, so we've generalized the examples, conclusions, and so let's now make a definition. Definition. Given a basis, B is equal to, and then we have n vectors in here, so B1 through Bn for Rn. The change of coordinates matrix is what we're going to call it, because that's exactly what it's doing. The change of coordinates matrix change of coordinates matrix from the basis B to the standard. So this E is the standard matrix. This standard. I keep misspelling standard. Standard. Standard basis in Rn is the matrix P sub B for the basis is just the columns are the vectors and the bases. So, if you ever are given an alternate basis in Rn and you want to convert this alternate basis into the standard coordinates, you just compile all of your basis vectors as the columns of a matrix and use that matrix to transform your coordinates, and it'll spit out standard the standard coordinates in standard basis. Okay. So, quick note is that you can go the other direction. Think about it. P sub B, our change of coordinates matrix, has to be invertible. Has to be invertible by the invertible matrix theorem. I mean, think about it. If these form a linearly independent set, then there's going to be no free variables, and we've guaranteed the existence of a solution already. So no free variables, guaranteed at least that one solution that's unique, ergo we can take its inverse and go backwards with it. So it is invertible. So that tells us that if I want to go the opposite direction and take the inverse of the change of coordinates matrix on X, I could do that to get to coordinates in the B basis. So say, okay, now I want to go the other direction. What if I want to start with the vectors in my standard basis, so the generic default understanding? I take the inverse of my, so I compile all of these vectors together, I get that matrix. Then I calculate its inverse, however you want to do that. We have multiple methods by now in the class. Calculate the inverse, and now you can use that inverse to basically send normally represented vectors into a completely different perspective, into a completely different type of coordinates. So this would be sending like a standard grid to this. Okay. So let me write these last two little things down. There's a theorem. Let my basis be B1, Bn, be a basis for a vector space V. Then the coordinate mapping x to then x represented with b coordinates instead of the standard coordinates. Is an isomorphism. You might be like, what on earth is an isomorphism? Glad you asked. Let's define that, because we'll need to know. A one-to-one. Okay, remember those two properties, one-to-one and onto? Isomorphism is basically like, hey, wouldn't it be super cool if you basically had both of those properties, like a transformation that was not only one-to-one, but also onto? If you have both, that's special. Let's call that isomorphism. So that's all that's going on here. A 1-to-1 linear transformation from a vector space V onto a vector space W is called an isomorphism. So to state that this is an isomorphism, all we're saying is in one word we're saying, hey, it's going to be one-to-one and also onto. That's all the jargon's saying, okay? Alrighty, this has been very, very long, and I'm sorry about that. But there's some very good explanations. I wanted to really take the time and visualize some of these things for you because it helps understand, hopefully. And also the proof needed to take some time. So, I will see you all on Monday.